Good day. For those of you who do not know us, we are the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to look at classes, encapsulation, and constructors. So, in this lesson, we will discuss constructors for rational numbers. We will describe normalizing rational numbers. We will describe member functions to access and modify the numerator and denominator. We will discuss authoring other functions and member functions on rational numbers. We will describe how to do operator overloading using member functions. We will discuss assignment, copying, and the need for a destructor. Finally, we will conclude by looking at a static member function. At this point, you now have seen how to author a class with member variables. However, you're also aware of the need for encapsulation. This requires member variables to be inaccessible, for if a user ever has access to changing a member variable, then it may be possible the user may place the object in an inconsistent state or perhaps even corrupt it. You are, however, aware we must deal with the initialization of objects, and we will do this through constructors. You are aware that the users do need to access and manipulate objects throughout their lifetime, and that will be through member functions. And finally, we will need to clean up after objects go out of scope or are deleted, and this will be through destructors. Now, you've already seen various classes and seen how to use member functions. You may have noticed also that the initialization and cleanup process seems to be more or less seamless. The compiler deals with all of this. For example, you know nothing about the standard cout object and how it's designed, but you're getting more information on how to use it and how to control how it creates its output. You know nothing about how a string is stored inside an instance of the array class, but you can call them member functions to access and or manipulate the entries or the string or data stored within that object. You probably have no idea what's happening inside an instance of the standard set class, but it seems to have some powerful functionality. And you don't know how the exception classes store the string that is passed to the constructor, but you can access it through the member function what. However, you don't need to know how any of this is implemented. As long as you know what the member functions are and how to access and manipulate them, then you can deal with any of these objects. So we will start by modifying our rational number class. First, we will no longer allow users to access the member variables. So here is our new class, and this is subtly different. For now, the two member variables appear after a private label. Up until now, we've had this nebulous public label at the top of the class. Well, anything that appears after the public label is accessible to the user. Anything that appears after the private label may only be accessed by constructors, member functions, destructors, and friends. In theory, you can have as many such labels in your class as you wish. You can, first of all, anything that's declared before any label is automatically private. Then you can have a public label, and then you can have another private label for some private member functions and private member variables. And then you can have some more public stuff, and then you can have, well, you can actually have multiple private labels in a row. You can do all this. However, this will be our approach. We will use two labels. First, the public label, and after this, we will declare anything at all that every user can access. This comes first because this is information that is useful to everyone who is using this class. Once we've listed everything that all users can access, we will have a private label. Anything that is declared after the private label can only be accessed in the constructor, various member functions, destructors, and friends. The reason this comes second is because this is information that is only useful to authors of this class. Authors being either the original author or individuals who are tasked with either improving, changing, or bug fixing this class. Now, private member variables cannot even be initialized by the user. By default, if you initialize an instance of a class, all member variables are always initialized to their default values, be that 0, a floating point 0, a null character, or false. So for example, if Q is declared to be an instance of the rational class at this point, and we initialize it, then the compiler will simply ensure that both of its member variables are set to 0. We can't even do anything with this yet, but at least we know that memory has been allocated for 2 ints, and each of them has been set to 0. Now, private member variables can also be instances of other classes, in which case their default value is whatever the default value is for that class, if the class has a default value. So for example, the default value of an instance of a string class is the empty string. So for example, in this class, if you were to create an instance of a person, then the first 2 member variables would become empty strings, while the balance of the member variables would be assigned 0. Now, we have a problem with our rational number class. The default value is exactly what we don't want in the rational number class, because the default denominator is 0, and 0 over 0 is not a rational number. If we want anything else other than the default values, we must define a constructor to initialize an instance of a class. That is, we must define a constructor to initialize an object. Now, a constructor is not like any other member function in a class. First of all, the constructor has the same name as the class. It is never explicitly called by the user. A call to the constructor is scheduled by the compiler, and a constructor has no return value. Consequently, I prefer to think of member functions being distinct from constructors, which again are distinct from the destructor. Constructors deal with the creation of objects. Member functions deal with how the user interacts with the class during its lifetime, and the destructor cleans the object up. So here is our rational number class, and we have declared a single constructor which takes no arguments. So there are no parameters to this constructor. It's public, which means that users will be able to have the compiler schedule calls to this constructor. Here is our version of the constructor for the rational number class, and we will go over how this works in the next few slides. Now, like all other functions in C++, constructors must be declared and defined. The constructor declaration is actually in the class definition, and it is simply the one line in that class definition that gives the name of the constructor and an indication that it takes no parameters. The constructor definition, however, appears after the class definition. So here is our constructor definition. Now, to begin, to indicate to the compiler that this is not the definition of a function named rational, but rather it is the definition of a constructor in the rational class, we indicate this by placing rational : before the constructor identifier. If you don't include the name of the class with 2 colons beforehand, the compiler will think you are trying to define a new function called rational, and it will give you an error as you did not specify a return type. Constructors do not have return types. However, all other functions do, and if the compiler simply thinks you are defining a function, it expects a return type to be specified first. And that's likely the error message you may get. Next, once we have specified that this rational constructor is in the rational class, we include a colon. And following this, all of the member variables together with any initial values. Now, the order of these member variables must be in the same order in which they are listed in the class definition. Technically, it's not an error, but we will require it in this class, and it will make your life a lot easier. Now, at this point, numer refers to that particular member variable in the instance of the object that's being created. So we are initializing a rational number, and its numer member variable is being initialized with a value 0. Next, its denom member variable is being initialized with a value of 1. Each member variable will be initialized one at a time, and in fact, subsequent member variables can use the initial values of previous member variables in their own initialization, and we'll see that later. Finally, there's the constructor body. This is a block of code that is executed after all member variables are initialized. Now, for our rational number class at this point, there's nothing more for the constructor to do. We've initialized the numerator as 0, and we've initialized the denominator as 1. This rational number is already in normal form. Let us now write 2 member functions that can return the numerator and denominator values of a rational number respectively. Because users will be using these member functions, they appear after the public label in the class definition. Now, we're now going to introduce something else. There's a const that appears after the declaration. Well, actually, it's part of the declaration, but it is the last keyword in that declaration. This indicates that this member function cannot change any of the values of any member variables of the object they are being called on. We can now define these member functions. Remember, member functions are declared in the class definition. Member functions are defined after the class definition. Now, anytime you refer to any member variable in a member function, those member variables automatically refer to the member variables of the object on which the member function was called. Let's take a look at this. We can now use these member functions. So here, Q is declared to be an instance of the rational class, and it is initialized with the constructor. We can now print to the screen the numerator, a slash, and then the denominator. So when we call numer and we then refer to the member variable numer, that refers to the member variable of Q. The same for denom. The output is 0/1. Now, recall that in this main function, Q is a local variable. That means the memory allocated for Q by the compiler, which is 2 integers or 8 bytes, then that memory is cleaned up once the local variable goes out of scope. That is, when it goes out of scope, those 8 bytes on the stack may be reused by another routine. Now, at this point, we can even implement the printing of rational numbers. So we are overloading the left shift operator so that if the first object is an O-stream object like cout and the right-hand operand is a rational number, then we will simply print the numerator of that rational number followed by a slash followed by the denominator. We then return by reference that O-stream object. So now we can already use this. We have declared Q to be a rational number, and now we will print Q to the screen. This will call the above function, not member function, and that will print 0 divided by 1. Now, can we improve this output? Well, this is a nice little modification. We always print the numerator, and because we will ensure it is always in normal form, only the numerator can be negative. Then we will print a slash and the denominator only if the denominator is not equal to 1. So therefore, if this rational number represents an integer, such as 3/1, we will just print 3. On the other hand, if the denominator is not 0, we will then go ahead and print the denominator after a slash. So if the denominator is 1, the rational number is printed as an integer, and in this case, we will simply see 0 printed to the screen. Now, alternatively, we can also define more than one constructor, and those constructors can have parameters. These parameters can also have default values. Now, you will recall, as with functions, default values must always be given in the declaration. And the declaration of a constructor is in the class definition. So we've already authored one constructor that takes no arguments. We will now create a constructor that takes 2 parameters, numer and denom, and denom has a default value of 1. Now there's a little bit more work to do and a few design decisions. Question: what happens if the second argument is 0? That is, they are declaring a rational number with a 0 denominator. Do we hide the error and just set the denominator to 1? Well, hiding errors is often a mistake because this is explicitly allowing the user to make mistakes without acknowledging that. And so what the code does isn't really what you expect. It's going to be very bizarre if you can initialize a rational number with an initial denominator of 0, but it's not really a denominator of 0. So the domain for the denominator is any non-zero integer, and therefore, if we will initialize both the numer and denominator member variables with the 2 arguments, and then we will check. If at this point the denominator member variable is 0, we will throw an exception. specifically a domain error, and we will give it the string the denominator must be non-zero. Now recall that we want rational numbers to be stored in a normal form. That is, the denominator is always positive and the numerator and denominator share no common divisors. However, we should allow the user to enter a rational number such as -15 over -10, in which case that should be simplified to 3/2. So now we will continue to use the body of the constructor to normalize that rational number. So let us add a member function that normalizes a rational number. Now, first of all, users should really not access this function, so we will declare it after the private label. These functions are sometimes called helper functions. They are meant to be used by other member functions, not the user. Also, you will notice that unlike the numer and denom member functions, this function is not declared const because we expect the normalize function to perhaps, if necessary, change the values stored in the member variables. So here is our implementation of the normalize member function. Again, the name of the function must be prefixed by rational : to indicate that this is actually a normalized function associated with the rational class and is just not an arbitrary function that has the name normalize. Now, the first thing we do is we make an assertion that the denominator is not equal to 0. Why is this an assertion rather than a test with throwing an exception? Because at this point, we should never be calling the normalize function with a denominator that is 0. If at this point the denominator is 0, we have a problem. There's something wrong in one of the constructors or one of the other member functions. Next, we check if the denominator is negative. If it is, we just negate both the numerator and the denominator. That is, we multiply by 1, which is -1 over -1. We then calculate the GCD and divide both the numerator and the denominator member variables by that divisor. Now, for now, let us assume that there is a GCD function implemented somewhere else. Later on, we will see how we can integrate such a GCD function into the rational number class. Now, how is this being used inside the constructor? Because after all, up until now, every single member function must be called on an object. So why are we not calling something .normalize or something similar? Well, just like if we ever reference a member variable inside a constructor, member function, or destructor, it is assumed that that member variable is one associated with the current object that is being constructed or being called on. The same thing is if you call a member function inside a constructor, member function, or destructor, it is assumed that this member function is being called on the same object we are currently working on. So we are constructing a new rational number, and normalize is being called on this same rational number. So when normalize changes the numerator and denominator member variables, it will be the member variables of this object being constructed. We can now use this constructor that has two parameters. So now when we declare p to be a rational number and we initialize it with two values, -10 and -45, this now calls the constructor that has two parameters, and these are the two arguments for those parameters. Inside the constructor, the two member variables will be assigned -10 and -45. The normalize function will be called, and ultimately now p has stored inside of it a numerator of 2 and a denominator of 9. So if we now print this rational number, we get the output 2/9. You can have as many different constructors as you wish, but the compiler must always be able to determine exactly which constructor you're calling. Suppose, for example, we have the constructor that takes no parameters, which we've already defined to just return 0/1, but then if we have a second constructor where both the first and second parameters have default values, then the compiler is going to be confused. If you create a rational number and do not pass any arguments to the constructor, does it call the first or the second? Rather than trying to guess what you mean, the compiler will just signal an error. It cannot distinguish which constructor should be called. So either you can have two constructors, one with no arguments that creates 0 divided by 1, and then a second one where the first argument must be supplied, or you can just have a single constructor with both the first argument having a default value of 0 and the second argument having a default value of 1. But you cannot have both simultaneously. The compiler must be able to distinguish between which constructor to call based on the arguments that are being passed. Next, let us write two member functions that allow the user to change the numerator or denominator. Now, as before, when we were accessing them, we simply used the name of the member variable without the underscore to be the name of the function when we were accessing them. We will do the same here, but now we will have an additional parameter. So now the compiler will know which one to call. If we call numer on an object with no parameters, then the compiler assumes we want to call the first function. If we call numer with an integer value, then it will call the functions we are defining now. So here's our implementation of both numer and denom, where we will change the values of the numerator and denominator. So first, for the numerator, we set the numerator to be the new numerator, and then we call the normalize function, because after all, if we've changed the numerator, it may be that the numerator and denominator no longer have a greatest common divisor of 1. Now in denom, it gets a little bit more interesting. First, we will check if the new denominator is 0. If so, we will throw a domain error exception, indicating that the denominator cannot be set to 0. If this is not true, then we will set the denominator to be the new denominator, and we will once again call the normalize function. Now, this is interesting. We have thrown an exception. If that exception is thrown, then it may also be caught. Yet, if that exception is caught and dealt with, the denominator has not yet changed. So we have not changed the denominator to 0, so therefore, if the exception is thrown but subsequently caught, the rational number on which this was called has not been yet set into an inconsistent state where the denominator is 0. So we caught the error before we changed the rational number. Now, suppose we want to implement an absolute value function for rational numbers. Question is, do we want to implement it as a member function or just a function? So, for example, here I have a rational number, -5/17. Do I want to be able to call the absolute value function on the rational number q? Or do I want to call the absolute value member function of q? Now, each of these will be implemented differently. If we are just authoring a function that takes a rational number as an argument, this is not at all associated with the rational number class. It's just a function. And in this case, it will take one argument, that being a rational number. It will then return a rational number where we find the absolute value of the parameter q's numerator, and the denominator, assumed to be positive, will remain unchanged. If, however, we want to implement it as a member function, it will take no arguments because it will be called on an instance of the rational number class. In this case, we just return a new rational number that has the absolute value of the numerator as a first argument and the denominator of this object to be the second argument. Many users who are starting out with C++ want to use the way they would think about it in high school. The preference in C++, however, is to use the second. Please don't buck the trend. It's a waste of your time because sooner or later you will probably migrate over to the C++ and object-oriented way of doing things. Now, how about operator overloading? We've already seen how we can overload the sum of two rationals so that the compiler will schedule a call to this particular function here. Now, we've changed the class so that now the numerator and denominator are private, and there is no relationship between this operator plus and the class. It just so happens that the two operands are rational numbers and the return type is a rational number. But this function or operator is not associated with the rational number class. Consequently, this function can only call the member functions that are public. All right, so now we change it slightly, so we take the numerator of the first times the denominator of the second plus the numerator of the second times the denominator of the first, and as the second argument, the product of the two denominators. This could work. However, we can also implement operator overloading with a member function. Now, if you have a member function plus that takes a rational number as an argument, then the compiler assumes if you ever call p plus q, then this member function will be called on the left operand and the right operand will become the argument to this function. All right, so this, first of all, this member function must be declared inside the rational number class, and it must be defined after it. You'll notice that we include rational double colon operator plus. So this is the operator plus associated with the rational number class. Now, when you refer to numer or denom as a member function, that member function is called on the left-hand operand, because that is the object on which this member function is being called. If you want to refer to Q, this right-hand operand, you must explicitly refer to Q's numerator or Q's denominator. All right, once again, the preference in C++ is to use the second, where the operator plus is overloaded as a member function. Again, don't buck the trend. Now, question. The member function we just saw for overloading operator plus has numer called as a function, as opposed to, as we see here in the second example, numer and denom member variables being explicitly called. Which is better? Well, my advice is if you are simply accessing a member variable and there is a function that does exactly that, then it is best to call that function, because you're guaranteed you cannot accidentally assign to that member variable. In the second case, a small programming error may accidentally assign to either the numer or denom member variables. So in the first, we are guaranteeing that we cannot assign to them. Now, some of you who are more in tune with programming are saying, well, in the second, we're just having accesses to member variables. That's very fast. On the other hand, the first requires 6 function calls. Function calls that require something to be put on the stack and something to be returned. Isn't that a waste of time? Well, fortunately, today's compilers are reasonably intelligent. And most compilers today, even if you gave it the code in the first, which protects you from accidentally making a mistake, will automatically compile that as if it was the second, because it will simply look at the functions and say, well, this function just returns the member variable. So it will literally replace the function call with that member variable. So let the compiler deal with optimizations. What you want to do is you want to write code that is safe. Consequently, the only time you should ever actually have an explicit member variable is when it is being assigned to. So here is a better implementation of the normalize member function. You will notice that in this implementation, if we are simply accessing the numerator or denominator member variables, we call the corresponding member function. Only when we assign to a member variable do we actually use the name of that member variable. One of the nice features here is, suppose you wanted to have a condition if denom is equal to 0. However, if you just use the member variable denom, unfortunately you made a typo. You said if denom is assigned the value 0, so now denom actually is 0, then something is done, and that something actually never gets done in this case. If, on the other hand, you tried to assign to denom as a function call, the compiler would signal an error. You cannot assign to a function call because it's just returning something. So Doing this actually allows you to catch potential errors such as the one shown here. Now, what happens if the user has you adding an integer onto a rational number? Well, we can implement this as a member function. So if the compiler sees p being a rational number plus 3, which is an integer, then this overloaded function has an argument that is an integer. So it will call this member function on the first operand. So this is if you do rational plus integer. And then it will calculate the result as appropriate. And of course, because an integer is just the rational number of that integer over 1, it's a reasonably straightforward calculation, and the constructor will divide out any common divisor between the numerator and the denominator when this new object is constructed. Problem: what happens if you have an integer plus a rational? Unfortunately, C++ doesn't know anything about the properties of rational numbers. So C++ does not know that a plus b for rational numbers equals b plus a. So for this case, you have to explicitly declare a function outside of the rational number class, which will then calculate the sum of an integer plus a rational. Now we could implement this, but instead we're going to implement it by just calling q plus n. So n plus q will be evaluated as q plus n. But now q plus n will call the first function we see above here because q is now a rational number and the right-hand operand is now an int, and so it will happily go up to the first function, calculate that result, which will then return the sum of q plus n, and that same result will be returned by this function that calculates the sum of an integer and a rational number. So this is getting a little bit subtle, but hopefully you're okay with this. So let's review our class definition so far. Initially, we have to declare rational to be a class. Once we have declared rational to be a class, we can declare an operator plus that takes an integer and a rational number as operands. Then we have the class definition, and so now we see that we have two member functions, operator plus where the right-hand side is a rational number, and operator plus where the right-hand side is an integer. We also have the absolute value function. Now all of these are constant because none of these will change the rational number in question. And down at the bottom we have our private member functions and our private member variables. So how about unary plus and unary minus? Well, again, these can be implemented as member functions and so must be declared in the class definition. However, looking at their implementation or their definition, we see that plus simply returns the rational number. Also, where would you see plus? Well, you might see it as in p plus plus q. Personally, if I were you, I'd really put parentheses around the plus q if you meant that. The same thing for unary minus. Negative q should evaluate to the additive inverse of q. So negative a over b. So you might see this in code as follows: p plus negative q. In this case, the unary minus operator is implemented as a member function, and so if you call negative q, it will call this function on q. And of course, it will return the negation of the numerator over the denominator. We can now implement subtraction. So for example, if we are calculating p minus q, then that will call the member function operator minus with q as the argument. Well, what we can return is actually operator plus on this object with the argument, the unary negation of q. So remember, operator plus is simply a member function, so you can actually call it explicitly by its name. This isn't seen very often, but this can be done. The same thing is if you are calling operator minus where the right-hand operand is an integer. So in this case, we just call the operator plus on this object with the negation of that integer. Finally, if we want to write a function that calculates an integer minus a rational number, let's just swap the order, negate q, so that will call the unary minus operator, or the negation. Whatever is returned on that, the member function operator plus will be called with n as an argument. So that will happily add negative q plus n. Now, if we make the comparison operators member functions as well, life becomes a lot easier. So if you compare two instances of a rational number class, it will then call operator equals as a member function on p with q, the right-hand side, being the argument. Well, now we will simply compare. Are the numerators equal and are the denominators equal? This is a lot easier because before we had to calculate if we were comparing a over b and c over d, we'd have to see that a times d equals b times c, because we had to cross multiply, because we did not know if the numerator and denominator were in lowest terms. Now, however, as we are guaranteed that p and q are in normal form, they are equal if and only if, well, they are equal if their numerator is equal and their denominator is equal. And that's the only time that they are equal, in normal form. Now, if we compare a rational number and an integer, then we will call this member function on that rational number with the integer as an argument. So now I'm going to check, hey, if the denominator of this object, the left-hand side, is 1, and the numerator is equal to n, then they're equal. Notice that this ends very quickly if the denominator is anything other than 1. If the denominator is not 1, then those two values cannot be equal. So that's more likely to be false. So that's why I put that one first. But nevertheless, this still is a nice, easy comparison, because if it is in normal form, the denominator must be 1 if it is actually an integer. Also, if you compare an integer with a rational number, we're just going to return the rational number compared to the integer. And that is going to call the previous member function on what used to be the right-hand side of that comparison. So we've already done the work. Let the previously implemented member function do that work. Now you'll notice the first two are member functions, but the last is just a function. And so technically that function is defined outside of the class and is not a member function of the class. Also, if we are comparing if a rational number p is less than a rational number q, if p is a over b and q is c over d, then you would just check if a times d is less than b times c if both denominators are positive. However, now that we're guaranteed that every rational number will be in normal form, we are guaranteed that the denominators are positive. So now the implementation of comparing two rational numbers is much easier. Also, if we are comparing see if a rational number is less than an integer, well, once again, we just assume that the integer is n over 1, and therefore a rational is less than that integer if the numerator is less than n times the denominator of that rational number. Now, if we compare if n is less than q, well, we haven't yet implemented q is greater than n, so instead we will just create a rational number n over 1 and compare that with q. That will now go back to the first implementation we see above, as it will create the rational number n over 1, and then on that it will call the member function less than with q as the argument. Now, something else. What happens with assignment? Here I have p, q, and r initialized with three different rational numbers. P is negative 5/3, q is 3/5, and r is 1/2. So here I print out the result of p plus q and then p plus r. However, then I assign q the value of r. Notice I don't say q equals r. I say q is assigned the value of r. Well, what happens then? Well, by default, all the member variables are just copied over, and this is true even if they're private, simply because the user still does not have access to those private member variables. Now, q has the numerator and denominator of r. So now p plus q will evaluate to the same result as p plus r. So the output of these three printing statements are negative 16/5, p plus r, negative 7/6, and now that q is assigned the value of r, p plus q is the same result, negative 7/6. The values that were originally stored in the member variables of q are completely overwritten and they are gone. How about if we initialize a rational number with another rational number? Well, here I initialize p with negative 5/3 and q with 3/5. I then initialize r with the value of q. Well, as you may expect, by default, all the member variables are just copied over. So whatever the member variables of q are, those values are just copied over to r, and now r is technically equal to q. So here I print p plus q and p plus r, and I should get the same result. However, next I assign q the value of p. So all the values of p are copied over to q. So now if I print out p plus q and p plus r again, p plus q has changed. So because q now equals p, I get twice p, whereas r is independent of q, so r has not changed. Question: does a rational number require a destructor? Well, not really, because no additional memory is required, no cleanup is required. When you instantiate a member variable of type rational, the compiler knows it requires 8 bytes, and when that variable goes out of scope, the compiler cleans up those 8 bytes. so no destructor is required. Now, recall that previously in this topic we discussed the need for a GCD function in the normalize member function. Now, if we were running C++ 2017, we'd have such a function, but perhaps we're still using an older version of the compiler. So thus, we need such a helper function, but this helper function doesn't really need any member variables. After all, this member function is just going to take two integers and return an int. It doesn't care about any numerator or denominator. Now, here's an implementation of a GCD function. However, this one assumes that the first argument will always be the numerator and the second argument will be the denominator. Thus, we make an assertion that the second argument is strictly greater than 0. So this implementation is slightly faster as we are making that assumption. All right, so this is a member function of the rational class, but you will notice nowhere does it ever refer to either numer or denom as member variables. Also, it does not call any member functions. So because this function is completely independent of any instance of this class, we can declare the function to be associated strictly with a class and not with any one instance. This is done in the class definition by declaring the function to be static. Static member functions have less overhead when called than member functions. And also, at the same time, static member functions may therefore not access any non-static member variables or any non-static member functions. Now, we haven't discussed static member variables, but that will be in a future topic. Following this lesson, you now know how to make member variables private. You also know how to define constructors. You know how to author member functions that access and manipulate the private member variables. You also understand how to do operator overloading with member functions. You know the workings of assignment and initialization for classes, at least by default, and you are aware that the destructor may not always be necessary. In this case, we have only seen a constructor. You are also aware of static member functions. Here are the references, the colophon, and a disclaimer. Cheers!